Okay, we're going to test this series for convergence or divergence. So we're probably going to do the alternating series test because we have an alternating series. How can we tell? Well, that's because we have -1 to the n times b sub n. Also, if we had -1 to the n plus 1 times b sub n, or n minus 1 in that exponent, anything like that is indicative that we might want to try an alternating series test. Before we do that, though, we also have to technically check if b sub n is always greater than or equal to 0. So, is it always greater than or equal to 0 for all the terms in our series? And yeah, it is, because we're going to go from 1 to infinity. We're going to be plugging in larger and larger numbers into this. That's never going to be negative. So yeah, there's no reason to think we can't do our alternating series test. So what is our alternating series test? It has two conditions. If we pass both of these conditions, we can say that it converges, that the entire series as a whole converges. The first condition is that b sub n must be decreasing. B sub n should be decreasing. The second thing is that when we take the limit as n approaches infinity, of b sub n, this must equal 0. If it meets both of these conditions, we pass both trials, then we can converge. Okay? So first, let's check if it's decreasing. How do we do that? Well, we could take the derivative. We could take the derivative and find out if it's negative for large enough numbers, because after all we care about is its behavior near infinity. So let's find out if its derivative is negative. How do we take a derivative of a fraction like this? Well, we have the quotient rule. With the quotient rule, we take the derivative of the numerator. That would give us 1 over n. Then we multiply by the denominator, which would be square root of n. We subtract the natural log of n times the derivative of the bottom of the denominator, which is 1 over 2 square root of n. And then we have the denominator squared. So this is squared, which just cancels out the square root and leaves us with n. We can simplify all this now. We have square root of n over n, square root of n over n, and we have the natural log of n right there. The natural log of n. This one, I would like to divide the square root of n on the numerator and on the denominator. So we get 1 over the square root of n. Because remember, with division we subtract. So I divided the numerator and that gave us 1. I divided the denominator by square root of n, and that gives us square root of n, because that's like subtracting 2 halves minus a half gives you 1/2 for the exponent. So that's what we have there. Now we can divide this. So we divide this, and we would get, again, because we are multiplying in the denominator, that's like addition. So if we have 1/2 for the exponent right now, and we add 2 halves, that's going to give us 3 halves. So this becomes n to the 3 halves, and this becomes n to the 3 halves, because we multiplied that n there into that denominator because we're dividing by n. Okay, now we can actually subtract. We can get the same we can get the same denominator by multiplying by 2, like this. And now we can actually perform the subtraction. So we get 2 minus the natural log of n over 2n to the 3 halves, because we had a common denominator now. So now we ask, this is our derivative, we finally got it, and we want to find out, is this negative? Is this negative? And if you plug in 1, which is our first term, you're going to find out, actually, no, it's not negative, because that's going to give us natural log of 1 is 0. 2 minus 0 is 2. That's a positive denominator, a positive numerator. The denominator is always positive. That gives us a positive term. So can we say, no, it's not decreasing? No, we can't say that. We have to keep going. So what happens if we plug in 2? It's actually still positive. So it's not decreasing. But you can't give up yet. You have to look at its behavior near infinity. So a trick might be to just plug in a very, very large number. And if you plug in a very, very large number, you will realize that, yes, that's obviously going to completely destroy the capacity for this 2 to keep the numerator positive. Because you're going to be subtracting a very, very large number, and it's going to become negative. It's not going to be able to sustain that positivity for very long. 2 isn't a very big number, and infinity gives you a lot of room to really go out there. So if you go and plug in something like the natural log of a very, very, very big number, and you also plug that very, very, very big number into this, you're going to get a negative number. You're going to get a negative number, and it's going to be negative for it is going to be decreasing. It's going to be negative. The derivative is negative, which means that b sub n is going to be decreasing for large enough numbers. Because remember, the derivative indicates the slope. So if your slope is negative, that means your function is decreasing. You have a negative slope, your function is decreasing. So that's our situation. Yeah, we passed the first part of it. It is going to be decreasing. It wasn't decreasing at first, but for most of its terms it is. So we can say it is, because we care about infinity. So the second thing was, what happens when we take the limit as n approaches infinity? If we take the limit as n approaches infinity, we would get the natural log of infinity over the square root of infinity, which is just infinity over infinity. That's infinity over infinity, and that tells us that we can use L'Hopital's rule. L'Hopital's rule says take the derivative of the numerator and take the derivative of the denominator. So this is not the quotient rule. This, because we're taking limit and we got that indeterminate product, we can just take the derivative of numerator and bottom without the quotient rule. That's L'Hopital's. So we have 1/2, and we bring the 1/2 and subtract 1/2. That's how you take the derivative. So this would be the same as 1 over 2 square root of n. Multiply by the reciprocal, we get 2 square root of n over n. 2 square root of n over n. This is the same thing as having n over n squared, because notice that n squared in a square root is the same thing as n. So that's what that is. But now we have 1 over n. If we further simplify, 1 over n, even further simplify, the square root of 1 is just 1, so we're left with this. We can bring the 2 back into that numerator, and so we are going to destroy that 2 when we plug infinity into this denominator. We plug infinity into this, because we're taking the limit as n approaches infinity, and that will give us 0. So it is 0, we passed both tests. That means that this converges. We can confidently say that this converges.